Welcome back to the lecture. We will continue with the second part. That's about it. I think this is with this part I shall conclude the particle in a ring in a rather elementary introduction that I have given. Okay. So, we shall look at a little bit more from what we left, namely we have this the wave function being given by an exponential m phi or phi. I mean, I keep interchanging them, but you know what it means. And m is of course, we are taking positive values here 0, 1, 2, 3, etc. Okay. Now, the 0 is something that we have to consider a little bit later. Let us worry about 1, 2, 3 and as integers. Okay. If this is the wave function, what about its normalized form? A is a normalization constant, because we always concern ourselves with making sure that the wave functions are normalizable. Therefore, the square of the wave functions can be associated with the probability description and the probability density. In here, the normalization is done in the fashion in which I mentioned, namely all the values of phi for which the wave function is unique. For different values of phi, the wave function is different. It has one value for one phi, and of course, you know that that particular range is between 0 and 2 pi, because after that the wave function simply repeats itself. Therefore, this is the range, even though other values are considered, this is the range for normalization, different values. Therefore, what you have is psi star phi, psi phi, d phi between 0 and 2 pi, that should be made equal to 1 for normalization. Okay. Yes. So, if you do that, then essentially psi star phi is of course a star e to the minus I m phi, because we do not know what a is, whether a is real or imaginary, but we will write it as a star, and therefore, what you have is the integral is the absolute value of a square, okay, between 0 to 2 pi e to the I minus I m phi e to the I m phi d phi, that is equal to 1, and this of course is 1. Therefore, you have the absolute value of a square times 2 pi is equal to 1, because the integral of 1 d phi between 0 and 2 pi is of course 2 pi. So, you have a, we will take it as real as 1 by root 2 pi. This is the normalization constant. Therefore, the wave function psi of phi is 1 by root 2 pi e to the I m phi. It is independent. The normalization constant is independent of m, unlike the case of the harmonic oscillator, where you found out that the normalization constant is also a function of the quantum number n, because of the Hermite polynomials involved. Okay. This is the wave function. Of course, in rotational motion, the two things that we are concerned with is the rotational kinetic energy and the angular momentum of the particle. Now, if the wave function is given by this alone, as we have chosen, then it is possible for us to calculate the angular momentum j. Okay. Since it points in a direction perpendicular to the actual plane of the circular motion, and we shall call that as the z component, if we assume x and y as the coordinates of the motion of the particle or the ring that we consider, the angular momentum is in a direction perpendicular to that, and that you know is nothing but psi star, the operator jz, psi d tau, which in this case the operator is minus I h bar d by d phi. This is the angular momentum operator that you use to actually derive this result. Therefore, if you calculate that, you see it is exponential between 0 to 2 pi 1 by 2 pi, because you have psi star psi, therefore, it is a square of 1 by root 2 pi, and then you have exponential minus I m phi, you have minus I h bar d by d phi exponential I m phi d phi. This is psi star psi. I do not need the denominator because the wave function is already normalized. And it is easy to calculate this. This is minus I h bar, d by d phi is I m, therefore, you have minus I h bar multiplying I m, which gives you h bar m, and m is a quantum number, h bar is a constant. So, you can actually take that out. Therefore, you have h bar m times 1 by 2 pi between 0 to 2 pi e to the minus I m phi times e to the I m phi d phi, and that is of course, that is nothing but the normalization of this wave function itself. So, you get h bar m. Okay. So, the angular momentum is therefore a quantized quantity. Angular momentum is quantized. You already have derived the energy E as h bar square m square by 2 I. Thus, energy is rotational kinetic energy is also quantized. Is also quantized. I have been careful enough not to include the rotational, the potential energy. See, there is a potential energy, as I said in the last lecture. Rotational motion is an accelerated motion, it is a non-inertial motion. And the particle or the system keeps moving around a point only because there is a central force directed towards the center of the rotation. Therefore, the potential energy cannot be ignored. We have ignored it because we assumed that the radius of the system is a fixed value. And for that given radius, we found out that the energy is given by h bar square m square by 2 I. Where is the information on the radius? It is actually in the value of I, because that is nothing but the mass m times the r square, where r is the radius. Therefore, it is already given in here. If the radius is also a variable, then the potential energy is actually a function of the radius, and then whatever we have done cannot be done. You have to solve the full Schrodinger equation, in which there is the kinetic energy given by whatever we did, namely minus h bar square by 2 I d square by d phi square, that is one. Then you have to actually include the potential energy, and then it is a two-dimensional motion because it involves radius and the angle. That is something else. We will do that if we have to study rotational motion as an internal degree of freedom in spectroscopy. Here, we have not considered that. We have only worried about the rotational kinetic energy as the total energy, neglecting the potential energy, and then you find out that the angular momentum is given by h bar m, and that is a quantized quantity. What about if we use the wave function e to the minus I m phi, e to the minus I m phi? It should be obvious that if you calculate the angular momentum, it is obviously minus h bar m. Okay. It is a negative value. Okay. The angular momentum therefore has a directional sense either towards the perpendicular to the plane up or perpendicular to the plane down. But what is interesting is, what is if we use the general wave function, namely a e to the I m phi plus b e to the minus I m phi, because we do not know whether the particular motion is clockwise or anti-clockwise, we do not know what it is. then we also do not know what the value. The Jz is not a fixed quantity. Please remember, when you wrote the kinetic energy, h of psi phi was minus h bar square by 2 I d square by d phi square psi, and you wrote this as E psi. Therefore, you see that the Hamiltonian acting on the wave function, the Hamiltonian operator acting on the wave function gave you the wave function and the energy, and you remember that this was the eigenvalue equation. Therefore, the energy was an eigenvalue for this problem and the psi is an eigenfunction. Likewise, if you write to the Jz operator and write psi phi, okay, if psi phi is either exponential E I m phi 1 by root 2 pi or 1 by root 2 pi minus, 1 by root 2 pi exponential minus I m phi. If the wave function is either this or that, then you also see that the angular momentum Jz acting on psi phi gives you that angular momentum value, which is, as you remember, minus h bar d I h bar d by d phi 1 by root 2 pi exponential plus or minus I m phi. If I put that in, then you will get the answer minus or what do you get? Plus or minus, yes, plus or minus h bar m e to the plus or minus I m phi. Okay. So, the plus is for the plus and the minus is for the minus. Therefore, you see that the angular momentum operator Jz acting on psi gives you plus or minus, plus or minus h bar m psi, and I will write it as plus minus here to say the plus component is e to the I m phi, the minus component is e to the minus I m phi. Angular momentum is also an eigenvalue. Is also an eigenvalue. That is, h and the angular momentum are simultaneously quantized. And or observables and or eigenvalues of psi and have eigenvalues, simultaneous eigenvalues. If the wave function is not given by one or the other component of the exponential I m phi, okay, if the wave function is given by a linear combination of the two, these are the two possibilities. And the m of course takes different values, and therefore, the psi is for you have infinite number of wave functions and infinite number of energies for the particle fixed to a particular radius, because that radius fixes the value of I, the moment of inertia. Therefore, the energy is given by that unit h bar square by 2 I, that is the fundamental unit for that problem. But if the wave function is a linear combination of the plus or minus I m phi, then the angular momentum operator does not have an eigenvalue, because if you write psi phi is a e to the I m phi plus b e to the minus I m phi, if you write that, and you can normalize this, okay, if you try to calculate the expectation value, if you calculate Jz acting on this psi phi, please remember Jz is minus I h bar d by d phi on this wave function psi phi, and please note that this is going to give you the d by d phi acting on I m will give you plus I m, and therefore, you will get minus I h bar I m e to the I m phi with a, of course, and then you will have for the B, you will have minus Im e to the minus Im phi B. Okay. Therefore, you see that you are going to get Jz acting on A e to the Im phi plus B e to the minus Im phi gives you now H bar m times A e to the Im phi, but with a minus sign B e to the minus Im phi. This is psi phi. This is not equal to psi phi. This is something else. Therefore, you have an operator acting on a function giving you something else, not the function back. So, it is not an eigenvalue equation. What does that mean? Angular momentum does not have a precisely defined value if the wave function is a linear combination A to the Imp plus B to the Imp. Does that mean angular momentum cannot be defined? It cannot be defined as to have a unique value. An average value can always be calculated. An average value in quantum mechanics is essentially the wave function star the operator associated with the wave, measured value and acting on the wave function integral, you remember that. Therefore, the angular momentum does not have a unique value, but an average value of the angular momentum can always be calculated for such linear states, linear combination states, by the same thing 0 to 2 pi. You will have A star e to the minus Im phi, because this is psi star, plus B star e to the Im phi. This is the psi star acting on now with the operator minus IH bar d by d phi, okay, acting on the psi which is A e to the Im phi plus B e to the minus Im phi d phi. But please remember, this wave function we have not yet normalized. Therefore, we have to make sure that we write the psi star psi in the denominator, namely 0 to 2 pi A star e to the Im phi plus B star A star minus Im phi plus B star e to the Im phi, okay, multiplied by A e to the Im phi plus B e to the minus Im phi d phi. Okay. This is a very elementary integral. Anybody can calculate that. I think with all the mathematics that you have done so far, you should be able to calculate this. Okay. It's easy to see that this will give you, the denominator will give you okay, A square, absolute A square minus absolute B square. Okay. Sorry, plus B square, I guess. B star e to the, plus B square. Okay. But the numerator will give you something else. The average value can be defined, but an eigenvalue does not exist. What does that mean? That means that if the wave function, if the particle's motion is not very clearly known as anti-clockwise or as clockwise, then we don't know whether the angular momentum vector is pointing upward or pointing downward. There's an average value. That means you can only do this many, many times, and every measurement gives you some result, and then you take the average, and that's the sense in which the angular momentum plays a very definite role when you come to particle in a box, particle on a ring. I think this exists also in a particle in a box. If the wave function for a particle in a box is not a precise eigenstate of the energy, but it can be linear combinations of the eigenstates of multiple eigenstates of energy as you have here, you have a similar problem. Therefore, please remember, this is also the first instance in which I am giving you a slightly more difficult problem, that the eigenvalues and the expectation values need not have to be the same when the state of the system is not precisely defined to be an eigenstate. Is this state an eigenstate of the energy operator? this linear combination? Of course it is. Please remember, the energy operator has d square by d phi square, second derivative operator. The minus m which comes in when you operate the derivative on this function once, it's cancelled, it becomes plus m square. Therefore, you get the energy. Of course, that's how you solve the Schrodinger equation, and I gave this as a general solution. Therefore, this is a general solution. What you have written here, namely the a e to the im phi plus b e to the minus im phi that you have here on the screen. Okay? This is also an eigenfunction of the energy operator, but it's not an eigenfunction of the angular momentum operator. Therefore, particle in the box, particle on a ring, motion on a ring comes out with something unique. The probability here is a problem because psi star psi is constant, is 1. Therefore, it's 1 by root 2 pi, and the probability of finding the particle on a circle in any region is precisely proportional to that region, and it's a constant. It does not vary like what you have for a particle in a box. If you say psi star psi d phi is the probability of locating the particle between phi and phi plus d phi and phi plus d phi between, then you know that if the wave function is psi of phi is it's 1 by root 2 pi e to the im phi, then psi star phi psi phi d phi is 1 by 2 pi d phi, because the exponentials cancel each other. Therefore, you see that the probability is proportional to the part of the ring, the length of the arc in a ring that we look at. What is the total length of the arc on the ring? What's the circumference? 2 pi. Okay. Therefore, you see that the probability of locating the particle in any region is uniformly the same and is purely proportional to the length of the arc, unlike the particle in the one-dimensional box, where it's quite different. So there is a subtlety here. As long as the particle is moving on a circle, its probability of locating it in a certain region is simply proportional to the length of the region. And of course, the total probability is 1. Therefore, anywhere on the circle, if you want to calculate, you have to do for all values of phi. It becomes obviously 2 pi, and therefore psi star psi d phi between the entire region is, of course, that 0 to 2 pi, and that's equal to 1. So the probability does not come up with, but please remember, this is for e to the im phi. It's the same thing for e to the minus im phi. And I will ask you to calculate the problem, in a problem in one of the quizzes, what is the probability if it's a linear combination of the wave function. The mathematics is very simple. You should be able to do that. So particle on a ring has 2 or 3 important summarized results. One, let me write the final summary here. Kinetic energy, we wrote this as minus h bar square by 2I d square by d phi square. Operator, kinetic energy operator. Energy is h bar square m square by 2I, which if you have to write, it's h square by 8 pi square I m square. M is 0, 1, 2, 3, etc. M is equal to 0 is a perfectly acceptable quantum number here, because all it means is that the particle does not have a rotational kinetic energy. It stays somewhere on the circle. it does not violate the uncertainty principle, because if we say that m is 0, we say that its angular momentum is exactly 0. If the angular momentum is 0, please remember angular momentum is given by this operator minus I h bar d by d phi, and therefore, the angular momentum and the angular coordinate have the same relation like the linear momentum and the linear coordinate that you have for a particle in a one dimensional box. They satisfy a commutation relation. Therefore, the location of the particle cannot be specified precisely if we know the precise value for the linear momentum. The same thing here. If we know precisely the value of angular momentum, we do not know exactly where the particle is. It is anywhere on the ring. Therefore, it is as uncertain as the dimension that you are worried about. Therefore, uncertainty principle is not violated. So, m is equal to 0 is allowed, which means rotational energy is equal to 0. Particle is stationary, but you do not know on what part of the circle, what arc of the circle that it is in. So, the uncertainty rules are not violated in any way, unlike the particle on in a box, where since you do not have the possibility of the particle in a box having a very precise position and a very precise momentum, or for a particle in the ring, we do not have that problem. Okay. So, this is the other important variation from the particle in a box. And finally, the wave functions are given by a or b, if you want to write e to the plus r minus I m phi, and m is of course plus m is with the notation constant a. Essentially, it is 1 by root 2 pi e to the plus r minus I m phi, which is the normalization constant. So, these results are important, but this particular result will be very useful in what is known as the microwave or rotational spectroscopy. I do not know whether I will talk about that in this course, but the particle in a ring is an extremely important model for understanding the elementary rigid body rotations of diatomic and polyatomic molecules. Okay. Therefore, I hope I have introduced you to something slightly different from the usual the quantum results that you see. Particle in the ring is slightly more subtle than any other model, and that has to be kept in mind. Okay. Until then, thank you very much.